Now, the word conservative vector field comes from the physics that we like to talk about the conservative energy. Right? So if you do some work on some moving object, there's energy put in, right? And that energy gets added to the kinetic energy of the particle, right? So those things are conserved. So that's where this conservative vector field thing comes up. All right, so let me talk a little bit of physics behind all this. First, I guess I explained why this is work, but let me try to explain this again. So I explained that if F is a force field, then F dot dr over curve C gives you the work done by the force field. So here's a brief explanation what this is again. So you start from this work formula, which is Fd, W equals to Fd. And then you say, well, this is only true if the displacement is the same direction as the force, right? If so if your force is like that, but the particle is moving this way, how do you calculate the work? You do F times D times cosine theta, right? And that's why I try to use this to talk about dot products, because that's where the dot product came to be, right? And people invented dot products just to talk about this work. See, the convention is that F, if you don't write an arrow on top, that means it's the norm of the length of this vector F, right? And this is the length of vector D. And therefore, if you write down the formula F dot D is this times cosine of the angle between it, it's exactly this formula. Okay? So that's why this is work. But this still falls short because this is only true for forces that are constant, right? What if force is different as it's moving? Certainly that can happen, right? And that's when this comes into play. So here's what's happening here. So let's say you have some vector fields, and you have some kind of a force, some kind of a particle moving inside this force field. And we want to know how much work is done to this particle. Because apparently, if I look at this, there is work done to the particle, and it's going to speed up, right? If it went from here to there, what if the particle actually moved this way? Then it's going to slow down, right? Because the force is trying to do that. So it was moving this way, and the forces are against it, so it's going to slow down. That's because if you go this way, there's negative work done to the particle, and therefore there would be the kinetic energy will decrease. Okay? All right. So, anyways, let's say we're going this way. If we wanted to know the entire work, the idea is the following: divide the curve C into small parts, very, very tiny little things, so that you can talk about this small thing as the vector dr. Now, why is it called dr? Because that's a small difference, small change in the position, right? This is a change of something. So it's a very tiny little change in the position. And that's this vector. Okay? Now, the good thing about dividing this into tiny things is that when you divide it divide it to make it very, very small, then it looks like a straight line. And also, the vector field doesn't vary that much, and therefore the vector field can be thought as constant as it goes from here to there, just that tiny little bit. Okay? So at least on here, we can talk about the small amount of work done on this small interval, and that's same as using this formula. We can use this formula because F is almost a constant, and this is very small. It's almost a straight path. Okay? So we can say it's F dot dr. Okay? Now, how would you find the entire work then? This is the basic property of integrals, right? If you have any physical quantity, it's the sum of its parts, right? So work is some of these small work as you move on from here to just move in small amounts, right? And because this dW is F dot dr, it's this. Okay? So that's why work is this line integral, this integration over the pen. All right? All good? All right. Now, in the case when you have a potential function, then you can say something more about this work. So we're going to come up with some theorem that sounds reasonable in the physical perspective, and I hope to show you the proof in terms of mathematics. Okay? So let's think about the case when you have some kind of a potential function. Now, when do we have something like that? If you have a single charge at the middle, what happens? It gives you the electric potential, right? And if you put any kind of charged particle on that electric potential, you have the electric potential energy of that particle, right? Hopefully you remembered in physics too that those two things are different. Electric potential and electric potential energy. Right? Electric potential energy is only if you have the charge, because it's Q times V. But anyways, if you have this potential energy, right, then it means that there's force on every point of the space. Because if you have a single charge in the middle and then you have another charged particle, right, then this one will definitely be experiencing force, right? At any point, it's going to have force applied to this charged particle, right? The Coulomb's law says that they push each other, right? So there's this some kind of force acting on this thing. You might even remember this the formula for this. It's U equals to K times negative K times Q over R, right? That's the formula for the potential, right? And then what's the Coulomb's law? Oh, sorry, it should be Q. Because without the Q, it would be the electric potential. This is electric potential energy. And then if you want the force is the Coulomb's law, right? Force is K times QQ over R squared, right? And the relationship between these two is that you get this by differentiating this. Actually, what's happening is this is a vector, right? Whereas, so this is only the norm of this vector. Right? So the force is a vector that arises from some potential energy. And it's really the gradient of this thing. Okay? See, I'm trying to talk about physics a lot because in your engineering course, eventually you have to put all of these together. You can't just learn math here and forget, learn physics over there and forget. You not only have to remember them, but you have to know how these things are related. Okay? It's very important. Okay? So imagine something like this. You have some kind of a heel. You put a ball. What happens to this ball?
It will point on the hill.
It will try to go downhill, right? The steeper this heel is, the more force will be acting, right? And the force will always be directed to the fastest decreasing direction. Is that right? Okay. So what happens is that if you have a potential, then the gradient of U points to the fastest increasing direction, but the force is negative of the fastest it's the fastest decreasing direction, so it's the negative of this thing. Okay? So that's your force. Okay, so the vector field of force is given by taking the negative gradient of the potential. That's always true. Now, this actually gives us some very important theorem just from the physical inside. So think about the following. You have some heel, and you have some marble, okay? And you move, you put this marble here, and it rolls down. So initially, let's say you pushed it over there, so it has some initial kinetic energy, right? But as it goes that way, because it has to go downhill, it actually goes like this. and it stops here. It doesn't stop here, but it's passing through this point. Okay. So we can ask the following: if this is point A and this is point B, what's the meaning? First, question one is, what's the meaning of f dot dr on this path C? What's the meaning? I actually gave you the meaning, right? It's a work done by the force field arising from the potential, right? Okay. So this will be the kinetic energy gained by this procedure, right? Because it's the work done to the particle. Right? Now, if kinetic energy is gained, it must have come from somewhere. From where? Potential energy, right? The loss of potential energy will be the gain of the kinetic energy, isn't it right? Right. So this should equal to what? Negative of the change in the potential energy. That's how you learned it, right? So this is a gain of kinetic energy. Gain of kinetic energy is loss of the. That's what you learned. Remember this? Okay. All right. So let's see what that says. That's really negative of potential energy at point B minus potential energy at point A. Or, if you think about it, this is like negative of U at B minus negative of U at A. Now I'm going to, somehow physicists like to use this negative, but mathematicians like to use positive. So I'm just going to call F as negative of U so that this is now gradient of F. Okay? So in that case, what can I rewrite this using F? How does it get written in terms of F? Since negative of U is F, what do I write? F of B, F of A. Okay? And this is kind of awesome because we were trying to compute this integral using this parametrization. You had to divide by dt, and you had to put the t here, and we had to do all that work, right? But what's happening? If we can figure out the antiderivative, which is the potential function, like a potential function, it's actually negative of the potential function. But we forget about the negative. Just say, if we can find the antiderivative, what do? You just plug in the endpoints and you subtract. That's it. This is like the fundamental theorem for conservative vector fields. Okay? So here's what I'm trying to say. If your vector field is a gradient vector field of something, if your vector field is a conservative vector field, then computing the line integral boils down to just finding the antiderivative and plugging the endpoints. Very simple, right? Okay, so let's see what that means. So here's a quick example. We already figured out that this is a. We already figured out that this is a. No, there's 3x squared, right? This is a conservative vector field. Okay, this is the gradient of what? 3x squared y, right? If this is your f, then the gradient of this is this, okay? Suppose we integrated this over c dot dr, where r is given as t comma t squared with t between 0 to 2. What will be this integral? Well, the long way will be divide by dt, differentiate this, plug in these into here, and do all the computation. It's going to be quite long, right? But what does this say? It says, this theorem says, all you need to know is the initial and the final. What's the initial position? 0, 0. What's the final position? 2, 4, right? Right? 2, 4 is your final, right? So all you have to do is say 3x squared y, evaluate at the 2 points. 2, 4 is your final, initial is 0, 0. Subtract the 2. So 2 squared is 4, 4 times 4 is 16, 16 times 3 is 48, done. Okay? So you can calculate this in lightning speed compared to the previous one if it's conservative. Okay? Usually vector fields are not conservative, but in physical context, there are many cases where it's conservative. And the integral becomes very easy to compute.